Hello everyone, I'm Dongyu, a postdoc at MIT. It's my great pleasure to present our work MTV, Visual Analytics for Detecting, Investigating, and Annotating Anomalies in Multivariate time series. This work is co-authored with Sarah, Alexandra, and Kalyan. Time series data can be found in various applications, such as satellite and cloud servers. Anomaly detection as one of the most important time series data analysis tasks turns out to be very useful in many critical scenarios, such as for preventative maintenance of large devices. However, time series anomaly detection is never an easy task. We work with a satellite operation company and knows that domain experts have to spend a lot of time to identify unusual behaviors out of more than almost 30,000 signals just from one individual satellite to assess its health condition. We begin to wonder how to effectively monitor and analyze anomalies facing such massive amount of data. Several major challenges are identified in this process. Instead of simply using threshold-based method, domain experts want to use machine learning to find contextual anomalies. However, they don't know where to start because of limited machine learning experience. They also find it difficult to integrate their domain knowledge to figure out the pattern identified by machine learning models, but do not necessarily indicate a problem. When a list of suspicious events are identified, domain experts still need to spend much effort to investigate anomalies. They may need to switch between different platforms to perform such investigation, leading to a lengthy and error-prone process. So during this process, they also want to very easy way to document findings and communicate insights. We thereby developed MTV as the first prototype system to tackle the aforementioned challenges. We worked with 9 experts and followed an iterative user-centered design process as illustrated on the right figures to guide this development. So the first research questions would be, what design element should be considered for such a system? We use 5 factors to help us better understand the context of use. The tool is designed to support asynchronous collaborative analysis and is suited for decisions of low or medium risk and take at least a few hours. And it should be very friendly to non-technical users, but requires a certain amount of domain expertise. We then came up with 6 design requirements, including the use of machine learning, what to control, the need of an interactive visual interface, and its relevant functions, and finally a workflow for an easy teamwork. We realized the need of human-AI collaboration workflow and start to wonder how does it look like. We propose a possible workflow here. It starts with machine learning extracting anomalies, continues with user giving high-level input to machines about what to observe, proceeds with an overview first and details on demand exploration, and a fast in situ annotation strategies, and finally ends with enhancing the machine learning pipeline, forming a closed loop. We then start to think what is an effective system solution that enables such a workflow. We then propose MTV as our first prototype system solution. MTV's major focus is the iterative visual interface from step 2 to step 5. The details of step 1 and 6 are introduced in one of our other papers. Machine learning produces results and these results will be saved in a database. So MTV visualizes these results and allow users to select what to analyze through this landing page. Once you choose a group of signals, you will then go to this main page, on the top of which you can see multiple time series spanning several years. These time series share the same time axis and helps you compare what is happening during a particular interval. Machine learning identified anomalies are then overlaid and highlighted, which gives you a way to have a better overview of the distributions. To see a more detailed view, you can select the time interval to explore it in the panel below. To answer why did machine learning flag an interval as an anomaly, you may toggle Show Prediction button. The flow on the top shows how much the machine learning predicted value deviates from the real values. So the larger the deviation is, the higher likelihood of an anomaly. Time-series signals also follow periodic patterns. The right panel here uses the circular glyph designed to depict such recurring pattern, and a radius here depicts the value change from the first day of the year till the last day of the year. For example, here you may observe the glyphs from 2012 to 2016 are of very similar shapes, but the shapes got changed significantly after 2017. Identified anomalies are also layouts around the circles. This way you can compare how anomalies are distributed differently across different years. Here we use stock data to showcase the annotation function in MTV. You will be able to explore annotations that are made by other team members. With this filtering function, you will see the events with a certain text. Then you can go to the signal annotation view to quickly glance through all these events. The event order here is sorted by the time, which is like the orders used in the Foxtrot. You can also open one event to see the most recent annotations and discussions of this event. You can go inside one particular event and see more information about it. Also, you can assign tag to this event. There are 6 types of tags encoded in different colors. For example, if you have seen a similar event before, then you can use the yellow tag. The comment box here shows all the annotation history. You can post your own comments here. You are also allowed to edit the range of the current event, or just create your own event based on your own domain knowledge. Then assign the correct tags and save the result. Another major feature of MTV is the search function of similarity segments, which is supported by our novel shape matching algorithm. You select the event and simply hit this button, then you are able to see the most similar time segments of the current selected one. You can filter them with the sliding bar here based on the similarity score. Then from the list below, you can explore the detailed information of all the similar segments. The list here is sorted by similarity score, and when you select one segment, the corresponding one will be highlighted as well. You can then quickly assign tags to all of the events, or just assign one tag. After showing our system, the follow-up question is how to evaluate it. We conducted a user study with 6 domain experts from satellite operation company. They participated in 4 case studies, each containing 4 to 12 signals to analyze. The table below shows how many interactions and communications they have with the system. Every event here is discussed and tagged. We also know that the tags of some events are more than 1, which is a sign suggesting a good teamwork. 2 concrete examples are also provided here to show how satellite experts discussed anomalous events. We also conducted a user study with general end users. The result overall seems very positive. We also summarized many design lessons to guide future development. You can read our paper for more details. As a conclusion of our work, we contributed the following 4 items: a list of design requirements, a human-AI collaboration workflow, a prototype system, and a user study with many learned lessons. Thank you for listening, and I hope you enjoyed the presentation.